Charles Darwin is one of the most important scientists in human history, the man who gave the world the theory of evolution. But there was one single animal that genuinely tormented him, an animal so confusing that he once wrote in a letter that the sight of its tail feather made him feel sick. That animal was the peacock. For over 150 years, the peacock's spectacular tail has been considered one of the most stubborn, unsolved puzzles in all of biology. Recently, that changed. A new wave of research, combining biology, physics, and even nanotechnology, has finally started cracking open secrets about the peacock that most people, especially in the United States, have never heard about. To understand why this bothered Darwin so much, you have to understand what his own theory predicted. Evolution is supposed to reward traits that help an animal survive. Sharp claws, camouflage, speed, strength. Traits that help you live longer and escape predators. But the peacock's train breaks that rule in almost every way imaginable. It is enormous, some feathers stretching over 5 feet long. It is heavy, weighing in at around 300 grams of extra material the bird has to carry everywhere it goes. It is bright, colorful, and shiny, which should make a peacock incredibly easy for predators to spot in the wild. From a pure survival standpoint, this tail should not exist. Darwin was so troubled by this that it pushed him to expand his own theory, eventually proposing the concept of sexual selection, the idea that some traits evolve not because they help an animal survive, but because they help an animal attract a mate. Even with that explanation, the exact mechanics of how and why the peacock's train works the way it does remained a genuine scientific mystery for generations. Let's start with one of the most surprising discoveries, something most people never learn, even if they have seen 100 pictures of peacocks online. Those famous blue, green, and gold colors covering a peacock's feathers are not created by pigment at all. There is no blue dye and no green dye anywhere inside those feathers. Instead, the color comes from something called structural coloration, a phenomenon first noticed by scientists using early microscopes hundreds of years ago, but only fully explained through modern nanotechnology research. Here is how it actually works. Inside each feather barbule, researchers discovered a nearly perfect microscopic grid made of tiny rods built from a substance called melanin, spaced apart by transparent keratin, with microscopic air gaps threaded in between. This entire structure is only around 100 to 130 nanometers across, which is an almost unimaginably small scale. For comparison, that is smaller than the width of the grooves on a Blu-ray disc. This tiny repeating pattern is technically known as a photonic crystal, and it works by bouncing incoming light back and forth between the microscopic rods in a way that cancels out certain wavelengths of light and reinforces others. Depending on how far apart the rods are spaced, different colors get reflected back to your eyes. Slightly wider spacing might produce a shimmering green, while slightly tighter spacing produces a deep blue. Researchers even found that some of the brown sections of peacock feathers, a color almost universally caused by simple pigment in the rest of the animal kingdom, is actually also partly created using the same structural nanotechnology, which genuinely surprised scientists who assumed brown coloring always came from pigment. To prove this, researchers ran an experiment where they soaked feather samples in glycerin, a syrupy liquid that fills in the microscopic air gaps inside the structure. Once the air gaps were filled, the light bouncing properties of the structure changed and the reflected color visibly shifted. This confirmed beyond any doubt that the eye-catching colors on a peacock are essentially a biological optical illusion, an accident of geometry and light physics, rather than chemical pigment. In simple terms, a peacock is not actually blue. It is arranged in a way that tricks light into appearing blue. Now here is where the story gets even stranger, because color was only the beginning of the mystery. For decades, scientists could not fully explain how the pattern of eye spots on a peacock's train stayed so remarkably consistent. If you look closely at wild peacocks, adult males tend to have an oddly similar number of eye spots, typically somewhere in the range of 165 to 170. And the placement of those eye spots forms a strikingly symmetrical, almost honeycomb-like hexagonal pattern across the fan. For a long time, nobody understood why there was so little natural variation in something that should, in theory, be influenced by genetics and random mutation like almost every other physical trait in nature. A recent scientific investigation finally tackled this question directly, using preserved museum specimens to study the actual anatomical blueprint responsible for feather placement. Researchers discovered that the tiny feather follicles on a peacock's lower back, the exact points where each individual train feather originates and grows outward from, are arranged in a specific zigzag pattern. This zigzag blueprint essentially locks in the mathematical layout of the entire train before a single feather even grows. It dictates the symmetry of the fan, the hexagonal spacing of the eye spots, and even the concentric colored rings inside each individual eye spot. In other words, the peacock's train is not a random canvas shaped purely by mate selection pressure over generations. It is built from a strict internal architectural template, similar to how a snowflake structure is dictated by the underlying physics of how ice crystals form, rather than by random chance. This discovery matters far beyond simple biological curiosity, because it directly challenges nearly a century and a half of assumptions about female mate choice in peacocks. For years, researchers debated whether peahens were choosing mates based on how many eye spots a male had, assuming that more eye spots signaled better genetics or stronger health. But if the zigzag blueprint locks the eye spot number into a narrow, predictable range for essentially every healthy adult male, then eye spot count alone cannot be the main signal peahens are using to judge quality. This finding helps explain why earlier studies investigating eye spot number and mating success kept producing conflicting and inconsistent results. Researchers were searching for a genetic variation that, according to this new anatomical evidence, was never really available to select from in the first place. So, if the number of eye spots is not the deciding factor, what actually catches a peahen's attention? This question led researchers toward another discovery that had almost nothing to do with color and everything to do with motion. Scientists began using extremely high-speed cameras capable of recording hundreds of frames per second to study exactly what a peacock does physically while trying to attract a mate. What they found was a display method now referred to as train rattling. When a peacock wants to impress a peahen, he does not simply hold his massive fan still. He actively vibrates it, using his much shorter, less flashy tail feathers almost like a pick strumming across the base of the longer, more elaborate train feathers. Researchers measured this shaking rate at around 25 vibrations every single second. Here is the part that genuinely stunned scientists. When they mathematically compared how fast each individual train feather naturally wants to vibrate on its own, based purely on its physical length, stiffness, and weight, against the actual shaking frequency recorded on live birds, the two numbers matched almost perfectly. The peacock was not brute forcing his enormous feathers into motion through raw muscular effort. He was tapping into resonance, the exact same physics principle behind pushing a child on a playground swing. If you push a swing at precisely the right moment during its natural back and forth rhythm, even a small amount of force can keep it swinging higher and higher with remarkably little effort. Peacocks appear to be doing something almost identical with an entire fan of stiff feathers weighing hundreds of grams, timing their strumming motion to align perfectly with the train's own natural vibrational frequency. This discovery revealed something remarkable about the eyespots themselves. Researchers studying the feather microstructure under magnification found that the barbs surrounding each eyespot are held together by microscopic hook-like structures, similar in basic concept to the way Velcro grips together. During train rattling, these microhooks allow the surrounding feather material to ripple and shimmer dramatically, while the eyespot's central region stays comparatively still and stable. The visual result is genuinely hypnotic. The background of the fan shimmers and blurs with movement and shifting light, while dozens of eye spots appear to float steadily in place above it, almost like still photographs suspended over a moving, glittering ocean. Scientists believe this contrast between motion and stillness may be a major part of what actually captures a peahen's attention, rather than the fixed count of the eye spots alone. But the story does not end with light and motion. Around the same time, researchers were studying train rattling with high-speed cameras. An entirely separate research team made a discovery that added a whole new sense to the peacock's display, one that most people have never even considered. It began almost by accident when researchers noticed a captive peacock repeatedly thrusting his quivering tail feathers directly toward a wall, seemingly listening to himself. Curious about this odd behavior, scientists investigated further and discovered that peacocks generate infrasound during their display, extremely low-frequency sound waves that sit below the range of normal human hearing. This infrasound appears to be produced by the vibration originating at the base of the train, the same physical shaking responsible for the shimmering visual effect. Researchers believe this deep, rumbling frequency may serve two purposes at once, both warning off rival males in the area and potentially playing a role in attracting a female's attention. Since peafowl are believed to have the anatomical hearing structures necessary to detect these extremely low-frequency vibrations, similar to structures found in birds like pigeons. There is also a long-standing assumption that peacocks pay a massive physical price for carrying this train around, constantly sacrificing speed and flight ability in exchange for looking impressive. Researchers eventually decided to directly test this assumption using high-speed video cameras to record peacocks taking off both with their full display feathers intact and again after their feathers had naturally molted at the end of breeding season. Surprisingly, the results showed no significant difference in flight or takeoff performance between the two conditions. In other words, despite popular assumption, carrying this enormous, colorful train does not appear to meaningfully weigh down a peacock's ability to escape danger the way scientists had long assumed. There is one more layer to this story that rarely gets mentioned outside of academic journals, and it involves one of the strangest reversals in the entire history of peacock research. Back in the 1990s, a famous study suggested that peahens strongly preferred males with a higher number of eye spots, and that this preference directly predicted which males successfully mated more often. For years, this became the accepted explanation taught in textbooks. Eye spot count equals attractiveness equals mating success, a clean and satisfying story. Then years later, a separate long-term study using the very same population of peafowl at the same location attempted to replicate those original findings, expecting to confirm the same pattern. Instead, the results completely failed to reproduce the original conclusion. This newer research found no meaningful relationship between eye spot number, train length, and how successful a male actually was at mating. The scientific community was left with two contradictory studies on the exact same birds, and no clear explanation for why the results had changed so dramatically. Some researchers speculated the peahen population's preferences may have shifted slightly over time. Others wondered whether the original study's statistical methods had overstated the strength of the pattern in the first place. This is precisely the kind of unresolved contradiction that the more recent zigzag developmental research helps make sense of. If, as this newer study argues, adult eye spot number is locked into an extremely narrow range by anatomical development rather than shaped freely by individual genetic variation, then searching for a strong statistical link between eye spot count and mating success may have always been searching for a signal that barely exists in the first place, buried in a trait with almost no natural variation to actually select from. The researchers behind this developmental model propose something more nuanced instead. Rather than counting individual eye spots, peahens may actually be evaluating a combined package of traits all at once, meaning train length, feather condition, symmetry, the vigor and energy behind the train rattling display, and overall body condition, essentially reading the entire performance as one unified signal rather than tallying up spots one by one. Interestingly, the same researchers pointed out that older males, despite having more years to accumulate feathers, are not automatically the most attractive option, since advanced age can come with declining vigor and physical condition, meaning a peahen watching a vigorous younger male perform an energetic train rattling display may be reading far more into that motion than scientists ever gave her credit for. This helps explain an earlier discovery that had puzzled researchers for years. A study testing female attention by physically placing small stickers over the iridescent eye spots on live, displaying males, found that mating success for those males collapsed to almost zero. Clearly, something about the eye spots matters enormously to a peahen's attention. But combined with everything else, researchers have since discovered that importance may have far less to do with simply counting a number and far more to do with how those eye spots behave visually during a live display, catching light through nanoscale photonic crystals appearing to hover motionless above a shimmering, resonating blur of movement, all timed to a frequency the male's own feathers are naturally built to vibrate at. The eye spot is not just a static decoration to be counted. It might be better understood as the centerpiece of a coordinated physical performance, one that blends optics, mechanical engineering, and possibly even sound into a single unified signal. Taken all together, these discoveries reveal an animal engineered on multiple scientific levels simultaneously. Nanoscale photonic crystals bend and filter light to produce color without a single drop of pigment. A rigid, mathematically precise zigzag developmental blueprint locks the symmetry and eye spot count into place before a feather ever grows, quietly resolving decades of confusing and contradictory research about what females are truly judging. Physical resonance, the same principle behind a swing set, allows a heavy fan of feathers to shimmer with remarkably efficient motion. Deep infrasonic vibrations rumble out at frequencies invisible to human ears. And despite the enormous size of the display, the bird's flight ability barely changes at all. For over a century, the peacock's tail sat at the center of one of biology's most famous unanswered questions, a feature so strange it helped push Darwin toward reshaping his own theory of evolution. Today, thanks to high-speed cameras, nanotechnology, developmental biology, and acoustic research working together, scientists are finally beginning to understand the full picture behind this display, piece by piece. And in typical fashion for nature, the true answer turned out to be even stranger, more intricate, and more impressive than anyone had originally guessed.